Hello again. I want to show you how you can solve differential equations, simple differential equations using Laplace transforms. So I want to start actually by showing you the definition of what is the Laplace of a first derivative. Which is basically a formula. So if you have the Laplace of some function in the time domain, and this is the first derivative, so I'm using the dot notation to say f prime in a way. So this actually becomes f of s. So remember, when you go to the s domain, you use the uppercase, minus f of 0. So this would be actually the initial value of the function at t equals 0, the f0. Okay, similarly, the Laplace of second derivative, f double prime, is s squared, very similar, f of s minus s, f of 0, minus f prime, or f dot 0. So f dot is the condition on the derivative of f at t equals 0. Okay. So based on that, let's go ahead and solve the differential equations. That actually is a typical mechanical system consisting of a mass. So x double dot here is the mass, and x represents actually the position of this mass. So then we have a damper. The damper friction, the viscous friction, will give you, let's say, 6x dot. And these numbers are just the coefficient of different elements. And then we have plus 25x. Let's make this a homogeneous differential equation, so the right-hand side is 0. And then we disturb this system by some initial condition. Remember, x represents the position. So x dot, which is the position at t equals 0, is 1 inch, let's say, or whatever unit you want to use. And x dot 0, which actually would be the velocity, the derivative of position, let's say it's 2 inches per second. So these are called initial condition. We use IC. For them, I for initial, C for condition. Okay, so let's go ahead and try to find the Laplace of this homogeneous second order differential equation. Second order because the derivative of the highest derivative is 2. Okay, so we have to go and take the Laplace of this expression, or this equation rather. Okay, so the Laplace, remember now we're using x instead of f. So we get s squared using the formula up here, s squared x of s minus s x of 0 minus x dot of 0, right, plus 6. So now, because I have a 6 being multiplied by x dot, the Laplace of first derivative, as you could see here, is s x of s minus x of 0, and then plus 25 x of s equal 0. So now remember that x of 0 is equal to 1, x dot is equal to 2, and over here again x of 0 is equal to 1. So when you clean this up and you factor x of s, you end up getting s squared plus 6s plus 25 after you factor x of s. And then look, these minus s times 1 minus 2, and then a minus 6 here goes to the other side and becomes s plus 8 eventually. So now let's put our x of s, and this is by the way called the transfer function. We have s plus 8, which actually was generated due to the initial conditions, and then in the denominator we have s squared plus 6s plus 25. Now we want to go back to the time domain and have x as a function of time. That's the objective. So let me go to the next page and rewrite this for you. So our function in the s domain is s plus 8 divided by s squared plus 6s plus 25. So notice that the roots of the denominator, s squared plus 6x plus 25, and I showed this in another video, are complex. Roots are complex and complex conjugates. Therefore, we're going to use the method called completing a square. That's the easiest way to bring this back to the time domain. Completing a square means that if you take this value, the 6 here, and divide it by 2 or multiply it by 1/2, you get 3. Then take this 3 and square it, and it becomes 9. Now think of 25 as 9 plus 16. So if you go back and rewrite, let me go back to black, rewrite your equation in the denominator as s squared plus 6s plus 9 plus 16. So you see it's 25. But you see this s squared plus 6s plus 9 actually becomes s plus 3 squared plus 16. And now we can actually manipulate this and bring it to the time domain. So what I'm going to do actually here is rewrite this as, notice that this is actually what we call omega squared. So this can be written as 4 squared actually. So I would write this as actually s plus 3 plus 5 in the numerator, because I want to have the s plus 3 in the numerator, and you'll see in a minute why. So then this becomes 1 s plus 3 divided by this denominator, right? And then I have a 5 here over s plus 3 squared plus 4 squared. So basically I broke it into 2 terms. So now let me go to the next page and remind you of two the sine and cosine functions that we could use to go back to the time domain. So just a reminder that the inverse Laplace of something in this format, s plus a divided by s plus a squared plus omega squared, when you go back to the time domain, it becomes actually e to the minus at cosine omega t. And similarly, the inverse Laplace of s, just omega in the numerator divided by s plus a squared plus omega squared again. You go back to the time domain, and it becomes e to the minus at sine omega t. So now look, we have, this is a, right? And this is omega, and this is again a. It matches exactly what we have. The only problem is that we need a 4 here in the numerator, so that we can put actually multiply by 4 here and divide by a 4, and there is nothing wrong with that. So when we go back, let me actually rewrite these two expressions for you so you could see them over here. So remember, we had what? X of s as what? S plus 3 divided by s plus 3 squared plus 4 squared, right? And then plus a 5 over s plus 3 squared plus 4 squared. And a minute ago I showed you that you could put a 4 here and a 4 in the numerator and forget about the 5. So this goes back to the time domain. So your function in the time domain now becomes e to the minus 3t cosine 4t, right? Based on this. And then look, I'll now make this a 5/4, and this would become also e to the minus 3t sine 4t, the same frequency. So this is the outcome. And this is actually what we call an underdamped system, that you will have a decay envelope. I will show you this, the graphical representation of this in future videos. Thank you for listening.